In my previous class, I was discussing about the effects of van der Waals forces on the properties of substances. The properties were melting and boiling point. Okay, these were the properties discussed in the previous class. The effect of van der Waals forces on the properties of substances, like liquefaction of gases, deviation of real gases from ideal gas behavior. These are the properties, Joule-Thomson effect. Okay, now more important than the properties are the factors on which the strength and magnitude of van der Waals forces depend, which I will discuss today. Now, if you look at the factors on which the strength and magnitude of van der Waals forces depend, the first one is temperature. Now, temperature, the strength and magnitude of these van der Waals forces. Van der Waals forces are three types. One is Keesom, then there is Debye, then there is London forces. London forces are temporary. Keesom is dipole induced, dipole interactive forces. Debye is dipole induced dipole interaction, and this London forces is a temporary dipole induced dipole interaction. Now, the first factor is temperature. The strength and magnitude of these forces decreases with increase in temperature. So if you want to break the van der Waals force, increase the temperature. The second factor is called pressure. An increase in pressure increases the strength and magnitude of these forces. If you increase the pressure, definitely in these compounds where you can see van der Waals forces, the magnitude of the van der Waals forces also increases along with the strength. The third one is number of electrons present in molecules. Molecules having a large number of electrons. When a molecule contains a large number of electrons, this results in greater polarization, that means separation of charges within the sphere in the electron cloud. Thereby, this increases the strength as well as magnitude of van der Waals forces. That is the third factor, number of electrons. The fourth one is molecular size. Larger molecules are held together by stronger van der Waals forces. So you must remember these factors. This will be asked in the compulsory part where there will be multiple choice questions. Okay, so just remember in this manner. The first one is temperature, the second one is pressure, third one is number of electrons present in the molecules, and the fourth one is molecular size. And how to remember? With the rise of temperature, van der Waals forces also it is higher. Pressure, it is not higher, it is lower. Now, in the second case, if you look at the second case over there, uh, with the what you call increase of pressure, the van der Waals forces is also higher. The third one over there, number of electrons present. When a molecule contains large number of electrons, if the number of electrons is more, the strength of the van der Waals force is also more. And the molecular size, if the size of the molecules is bigger, it's bigger, then the van der Waals force is also bigger. So this is direct relationship, direct, but over here it is inverse relationship in the case of the factor which is called temperature. So I request you to analyze this systematically on your own and try to learn them properly. Okay, now, so this subtopic is clear. This subtopic is clear to all of you, I guess. Okay, now I want to move to the next topic in this chapter, a very, very important topic in this chapter, which is called geometry and shape of molecules. Now, with regard to geometry and shape of molecules, if you know, a molecule consists of two or more atoms linked together through certain types of forces which are attractive. Moreover, in a polyatomic molecule, I hope you can see the screen, boys. Can you see the screen? Can you see the screen?
Mhm.
Okay, so
Yes, sir.
moreover, in a polyatomic molecule, the constituent atoms get arranged in a definite geometric fashion around the central atom. This definite relative arrangement of the bonded atoms in a molecule is known as geometry or shape of the molecule. The molecules may be linear, they may be triangular, they may be square planar, they may be pyramidal or tetrahedral, triangular, bipyramidal or octahedral, depending upon the number of bond pairs, number of lone pairs, depending upon the ligands linked to the central atom. Okay, so they will have different shapes and molecules. Now, with regard to the study of the geometry and shape of molecules, there were plenty of theories. Many theories were there to find the shape of the molecules. And out of these theories, all the theories, valence bond theory, valence valence electron pair repulsion theory, not the valence bond theory, valence electron valence shell electron pair repulsion theory is one such theory for predicting the shape of the molecules, which we will discuss today in detail. Okay, so please pay a lot of attention. Now, moving to the next slide, with regard to the theory which is called valence shell, this is valence shell electron pair repulsion theory. So if you look at the word repulsion, electron pair repulsion, there are electron pairs which are lone pairs, so they repel each other very badly. So please keep in mind, LP means lone pair. What is LP? LP means lone pair. Okay, so lone pair repulsion, it is maximum, it is higher than lone pair bond pair repulsion. BP means bond pair, and this lone pair bond pair is still higher than bond pair repulsion of electrons in molecules. So you must remember this order. It is very important before we begin the valence shell electron pair repulsion theory. So remember, if the lone pairs are there, if there are two lone pairs on the central atom in a molecule, repulsion is maximum. That is why the angle which is supposed to be 180 degrees, it is supposed to be 180 degrees in this water molecule, it is repelled so badly that the angle is decreased down to 104.5 degrees exactly in the case of water molecule. So looking at the first point over here, water has two bonded hydrogens and two unshared electron pairs on the central atom. The two hydrogen atoms are also repelled by the two lone pairs on the central atom, which give the molecule a bent shape. After it has bent, the bond angle between each hydrogen atom is now 104.5 degrees exactly. Okay, so this is one example just to introduce you all the valence shell electron pair repulsion theory. This theory is fully dependent on the number of electron pairs which are lone or bonding pairs. Okay, so it is all dependent upon the lone pair repulsion, or lone pair bond pair repulsion, or bond pair repulsion. Among these three, the least repulsion is provided by the bond pair. So that means these bond pairs, they repel each other weakly. Okay, to a very small extent. Now just have a look at the next slide over here on your screen. VSEPR theory, just illustration, molecular shapes. A stands for the central atom. Capital X stands for an atom bonded to central atom A, and E stands for lone pair on A. Number one, generic formula AX, central atom and a bonded atom. Picture is AX. Bonded atom is 1, lone pair is 0, so the shape of the molecule is linear. It is linear. Example is hydrogen molecule. Hybridization is only S orbitals are involved in the formation of the molecule hydrogen. Bond angle is 180 degrees. If you look at the domain 2, generic formula is either AX2 or AXE. AX2 or AXE. E stands for the lone pair. So here you can see in AX2, central atom and two atoms bonded on the side. Bonded atoms are 2. Lone pair is 0. No lone pairs. It is again a linear molecule. Example is carbon dioxide. Hybridization is sp. I will talk about hybridization later on in this chapter. And hybridization in short means mixing of atomic orbitals. If the atomic orbitals like s orbital or a p orbital or a d orbital or a f orbital, they mix among each other to form orbitals having the same energy, then this mixing is called hybridization. Now here the bond angle in this case, it is 180 degrees. Then moving to the third domain, AX3 or AX2E or AXE2, two lone pairs, your one lone pair, your no lone pair. 3, 2, 1, you can see the shapes over here. Okay. 0 lone pairs, 1 lone pair, 2 lone pair. The shape, but the molecular shape, when there are no lone pairs, is trigonal planar. Otherwise, it is bent. Otherwise, if there are two lone pairs, it is linear molecule. Shape, electron geometry is given trigonal planar in all these three cases. Okay. Then examples is aluminum bromide for trigonal planar. For trigonal planar, SnCl2 or oxygen. Hybridization is sp2. Bond angle is 120. Bond angle is 120. It is trigonal planar like this. In the center, there is an atom. You can talk about A, and then one X over here, another X over here, another X over here. This way. This way. Okay. This is how you get trigonal planar, and the bond angle over here is 120 degrees. Then, if you look at domain 4, 4, AX4, 4 ligands, 3 ligands, 1 lone pair, 2 ligands, 2 lone pairs, 1 ligand, 3 lone pairs. So examples here, 4 bonded atoms, 3 bonded atoms, 2 bonded atoms, 1 bonded atom. If the bonded atom is 1, there will be 3 lone pairs. Bonded atom 2, 2 lone pairs. Bonded atom 3, 1 lone pair. If the bonded atom is 4, there is no lone pair. So shapes are molecular shape, tetrahedral or trigonal, pyramidal or bent or linear. But the exact shapes, electron geometry is tetrahedral everywhere. Okay, and the hybridization is, it is sp3. The angle, the bond angle is 109 degrees, 109 degrees 28 minutes, and tetrahedral shape is like this. Tetrahedral shape is like this. You know, if you put carbon in the center over here and then hydrogens on the other sides like this on the vertices of this tetrahedron, then you get a shape like this. Okay, this carbon is lifted from the plane of the 4 hydrogens towards you, this carbon. Okay, so that's a tetrahedral shape. Now this is just an illustration to give you an idea about the VSEPR theory. If you look at the number of lone pairs, if the number of lone pairs are increasing, the shape is changing, the molecular shape is changing. From tetrahedral is becoming trigonal pyramid, it is bending and it is becoming linear. As the number of lone pairs increases, the reason is the lone pair repulsion is higher. Now, looking at the next slide, geometry shape of molecules. The first question is, what is VSEPR theory? That is important to understand, because after explaining the theory at the end of the day, I find students asking, what is the full form of VSEPR? So the full form of VSEPR is valence shell electron pair repulsion theory. This model is often abbreviated as VSEPR, pronounced VESPR. VESPR. It is basically a model to predict the geometry of molecules. Specifically, VSEPR model looks at the bonding and molecular geometry of organic molecules and polyatomic atoms. It is useful for nearly all compounds that have a central atom that is not a metal. Central atom that is not a metal. An important point to keep in mind. Okay, over here. Now, that was an intro to the VSEPR theory in full detail. Now, let us look at some of the points with regard to VSEPR theory. Now, under the points of VSEPR theory, the postulates we can say, the shape of the molecule is determined by whom? By repulsion between all the electrons present in the valence shell. The electrons can be lone pairs in the form of lone pairs, or it can be in the form of bonding pairs. So the shape of the molecule is dependent upon the lone pair interaction, or lone pair bond pair interaction, or bond pair interaction. The second postulate, electron pairs in the valence shell of the central atom repel each other and align themselves to minimize this repulsion. That means they try to stabilize themselves by pushing each other, if there is a lone pair, they will push each other, repel each other, and then they'll come to a point of maximum stability. The third point is, lone pair electrons take up more space around the central atom than a bond pair. An important point. Lone pair electrons, they need more space around the central atom than a bond pair. The reason is they need more space for the electrons to move. Otherwise, if it is bonded, it is occupied. Lone pairs have no work. They are present without forming a bond. The next point is, lone pair attracted to one nucleus but bond pair is shared by two nuclei. So remember, lone pair is attracted to the nucleus of the central atom only, but the bond pair is attracted, it is shared by two nuclei of the combining atoms. And the next point is the minimum repulsion to the state, minimum energy, and the maximum stability of the molecule. So this point also becomes important. If the repulsion is minimum, if the repulsion is minimum, then the stability of the molecule becomes higher. So this is one important point in the VSEPR theory. Now coming in detail to the postulates of the VSEPR theory. It is very long, but it is in detailed over here. Going one by one to the postulates of the VSEPR theory. The first one, in a polyatomic molecules, molecules made up of three or more atoms are called polyatomic molecules. One of the constituent atoms is identified as the central atom, to which all other atoms belonging to the molecule are linked. That is the first postulate. The second one, the total number of valence shell electron pairs decides the shape of the molecule. So it is very important. The total number of valence shell electrons pairs, it will decide what will be the shape of the molecule. Will it be linear, or will it be trigonal planar, or will it be trigonal bipyramidal, or will it be tetrahedral, or will it be octahedral? It is all dependent on the valence shell electron pairs. The next point, the electron pairs have a tendency to orient themselves, to align themselves, to position themselves in a way that minimizes the electron-electron repulsion between them, whether it is a lone pair or a bond pair, and thus maximizes the distance between them. The next point, the valence shell can be thought of as a sphere. The valence shell is a sphere where the electron pairs are localized, positioned on the surface in such a manner that the distance between them is maximum. So we must remember the valence shell, it is a sphere where the electrons are present and they are positioned in such a manner on the surface of the electron sphere that the distance between the one electron pair and the another electron pair on the central atom, it is maximized. Next point, should the central atom of the molecule be surrounded by bond pairs of electrons, then the asymmetrically shaped molecule can be expected. That means a molecule which is not symmetrical, you can expect. Should the central atom be surrounded by both lone pairs and bond pairs of the electrons, the molecule would tend to have a distorted shape because of the repulsion between the lone pair and the bond pair. Now, these are the important postulates which you have to keep in mind. Besides that, the VSEPR theory can be applied to each resonance structure of a molecule. So we can apply this theory to the resonance structure of the molecule as well. The strength of the repulsion is strongest in lone pairs and weakest in two bond pairs. So this I have already told you. Lone pair repulsion, it is higher than lone pair bond pair repulsion, which is higher than bond pair repulsion. This you have to remember. Very, very important, what we call order over here. Then, if electron pairs around the central atom are closer to each other, electron pairs around the central atom, they are closer, they will repel each other, definitely. This results in an increase in energy of the molecules. That means the molecules become what? Less stable. If the electron pairs lie far from each other, the repulsion between them will be less, and eventually the energy of the molecules will be low, which means the molecules become more stable. Now, after these postulates, moving to the next slide, there are some limitations also, disadvantages, okay, which have been discussed over here. This VSEPR theory fails very badly to explain isoelectronic species, means elements having the same number of electrons. It fails to explain the geometry of isoelectronic species. The species may vary in shapes despite having the same number of electrons. The VSEPR theory does not shed any light on the compounds of transition metals. The structure of several such compounds cannot be correctly described by this theory. This is because the VSEPR theory does not take into account the associated sizes of the substituent groups. That means the groups which are attached to the central atom, their sizes are not taken into consideration. That's why it makes the lone pairs which are inactive. Another very important limitation of the VSEPR theory is that it predicts that halides of group 2 elements will have a linear structure, but it has been found experimentally that the actual structure of the halides of group 2 are bent, which is not been able to explain by the VSEPR theory. These are the limitations. Okay, now moving further, how to predict the shape of molecules by using the VSEPR theory pointwise. Remember, the least electronegative atom must be selected as the central atom. Okay, since this atom has the highest ability to share its electrons with the other atoms belonging in the molecule. That is the first point. So, electronegative atom must be the central atom. The second point, the total number of electrons belonging to the outermost shell of the central atom must be counted. So you have to count always the total number of electrons belong to the valence shell of the central atom. That is the second point. The third point is the total number of electrons belong to the other atoms and used in bonds with the central atom must be counted. So the other atoms which are linked to the central atom, electrons must be counted. These two values must be added in order to obtain the valence shell electron pair number, which is called VSEP number. For example, if we have carbon, carbon in its valence shell, it has 4 electrons. And if I bring 4 hydrogens this way, 4 hydrogens around the carbon atom this way. So now this is 1, this is 2, this is 3, this is 4. So the VSEP, the VSEP number over here becomes 4, because there are 4 electron pairs which are used to form bonds. So the VSEP number for methane molecule central carbon atom becomes 4. So this will be clear to you all in the next slide which I am presenting. Now, after the calculation of the VSEPR number, then we can get the idea about the shape of the molecule. So if the VSEPR number is 2, then the molecule will have a linear shape. It will be having a linear shape. Now, what is linear shape? What is linear shape? For example, if we have like this beryllium difluoride, BeF, over here another F. So this is a linear shape. This beryllium does not have any lone pairs. There are 2 electron bonding, there are 2 electron bonding. So this is a linear shape, and the bond angle over here becomes 180 degrees. So that's a linear shape. Over here, VSEP number is 1 plus 1, 2. Then if the VSEP number is 3, then it becomes trigonal planar. Trigonal planar, like in the case of beryllium, boron trifluoride. Boron, okay, trifluoride. 1 fluorine here, 1 fluorine here, 1 fluorine here. Boron trifluoride. VSEP number is 1, 2, and 3. Trigonal planar. Okay. Then VSEP number 4 means it is tetrahedral shape, like methane. Then number 5, VSEP number 5, it is trigonal bipyramidal. I will show you the shapes in the next slides to come. If the VSEP number is 6, it is octahedral. If it is 7, in the case of IF7, then it is pentagonal bipyramidal. Okay, so these are how to get the VSEP number and the shape of the molecules. Now, going to our next slide, the first one is linear shape of the molecule. The first one is linear shape of the molecule. In this type of molecule, we find 2 places in the valence shell of the central atom. They should be arranged in such a manner that the repulsion can be minimized, pointing in the opposite direction. So I told you example is BF. Okay. Then the next shape is trigonal planar shape of the molecule. In this type of molecule, we find 3 molecules attached to a central atom. Like I told you, boron trifluoride like this, fluorine, fluorine, fluorine. Okay, boron trifluoride linked like this. Okay, bond angle 120 degrees. So this is a trigonal planar. The boron and the 3 fluorines are on the same plane. They are on the same plane. They are arranged in such a manner that the repulsion between the electrons can be minimized towards the corners of an equilateral triangle. Okay, so example is boron trifluoride. This is the second type of shape. Moving to the next one, number 3, that is tetrahedral shape of molecule. In 2-dimensional molecules, atoms lie in the same plane which are connected to the central atom, and if we place these conditions on methane, we will get a square planar geometry in which the bond angle is 90 degrees, but this is not possible. Now, if we consider all these conditions for a three-dimensional molecule, we will get a tetrahedral molecule in which the bond angle between carbon, hydrogen, it is 109 degrees 20 minutes. So here, as I have told you, for a tetrahedral shape, this is a tetrahedral shape, carbon, hydrogen, hydrogen, and one more hydrogen over here. The carbon which you see in the center, it is towards you. This is lifted towards you. And these four hydrogens are on the plane of the paper, on the plane of this board. So the angle, the bond angle over here, it is supposed to be 109 degrees 28 minutes. Okay, so that is how a tetrahedral shape looks like in the case of methane molecule. It is not 90 degrees, it is 109 degrees 20 because the carbon is above the plane of the four hydrogen atoms. Now the next shape is trigonal bipyramidal shape of molecule. Here let's take the example of phosphorus pentafluoride, PF5. 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 Now if I draw PF5 this way, I can put a triangle. I can put a triangle. Okay, this is a triangle, and three fluorines over here like this, and one, it is linked this way, and one fluorine above the plane, another fluorine below the plane. Are you getting it? Another one fluorine above the plane of paper towards you. This is away from you. So that is phosphorus pentafluoride. Here, the repulsion can be minimized by even distribution of electrons towards the corner of a trigonal bipyramid. In trigonal bipyramid, three positions lie along the equator of the molecule, and the two positions lie along an axis perpendicular to the equatorial plane. That means these are perpendicular up and down. They are perpendicular to this equatorial plane. Okay, this is the fourth type of the shape of the molecules. Now, we will discuss the others later on slowly today. Now, have a look at the next slide. How to use the VSEPR theory to predict the shape of the molecules. So here, the most important thing you have to keep in mind is lone pair repulsion is more than lone pair bond pair. It is more than bond pair repulsion. So here, total number of electron pairs around the central atom is equal to half the number of valence electrons of the central atom plus number of atoms linked to the central atom by single bonds. For negative ions, add the number of electrons equal to the units of negative charge on the ions to the valence electrons of the central atom. For positive ions, subtract the number of electrons equal to the units of the positive charge on the ion from the valence electrons of the central atom. And then number 2, the number of bond pairs is always equal to the number of atoms linked to the central atom by means of single bond. So this is also one written material for you all to be able to predict the shape of molecules. But better than this, I will show you a shortcut slowly in the slides to come. Now, this is number 3. Number of lone pairs is total number of electrons minus number of, this you already know, so you can read through this on your own. Okay, this will help you for predicting the shapes. Now I move to the next slide, pictorial representation. The different geometries that molecules can assume in accordance with the VSEPR theory can be seen here in the below. If the number of electron dense areas is 2, 2 electrons here, 2 electrons here, that means electron dense area is 2. It is a linear shape. Number of lone pairs, no lone pairs. Okay, it is a linear geometry. Linear geometry. Okay, see. Okay, no lone pairs. If it is 3 electron dense areas, that means trigonal planar. Okay, no lone pairs. Okay, over here, if there is one lone pair, it becomes bent, like water molecule. What do you call water molecule? Correct. If it has electron dense area 4, 1, 2, 3, and 4, then the shape becomes tetrahedral, like methane over here or ammonia over here. If it is methane, it is tetrahedral. If it is ammonia, it is trigonal bipyramidal. And if it is water, it becomes bent. Okay. Then if it is electron dense area is 5, 1 over here, 2, 3, 4, and 5. That time we have trigonal bipyramidal. Okay. If there are lone pairs, its shape is trigonal bipyramidal. If there is a lone pair, then it is a sawhorse. You know what is a sawhorse? Chakale chukule. Have you heard of chakale chukule in Nepali? And if you go to the park, you see there is a sawhorse.
Yes, sir.
Okay. Then after that, If there are two lone pairs, then it is T-shaped. If there are three lone pairs, it will become linear again. Then if the number of electron dense areas becomes 6, 1, 2, 3, 4, 5, and 6, the electron pair geometry is octahedral. If there are no lone pairs, it is octahedral, otherwise square planar for one lone pair. If there are two lone pairs, square planar. If there are three lone pairs, T-shaped. If there are four lone pairs, then it becomes linear in shape. So this chart becomes very, very important one for you all to summarize on the basis of VSEPR theory the different geometries of molecules depending upon the number of lone pairs. For one lone pair, for two lone pair, for three lone pair, for four lone pairs, there are different geometries or different shapes. Okay, now looking at the next slide, let us go in detail now. Let us look at this one. Geometry shape of molecules. Shape of beryllium difluoride molecule, which I was talking that time. This beryllium difluoride contains bonding pairs only. Example is here, beryllium difluoride. No lone pair, so the shape is linear. Okay, the shape is linear. Do not look at this. This one I have just put for the sake of illustration only over here. Beryllium difluoride is linear, but apart from that, you can have a look at carbon dioxide, which is linear. But as soon as lone pairs enter, then the shape becomes bent. It becomes trigonal bipyramidal. It becomes trigonal planar. It becomes T-shaped, depending upon the increasing number of lone pairs. Okay. Now this was for beryllium difluoride without any lone pairs, only bonding pairs. Then the next shape is for shape of boron trifluoride, molecules containing bond pairs only. Second example. So boron trifluoride, I told you that time also, it has a trigonal planar geometry. Trigonal planar geometry on the same plane. Okay. Then moving to the next one. Again, molecules containing bond pairs only. Shape of methane, CH4. I could not type this way, CH4. Please try to understand. Okay, it is CH4. Molecules containing methane. What do you call bonding pairs only. Example, methane. If it is regular, you have a shape like this in 2 dimensions, but this one is in 3-dimensional geometry. Okay, the carbon, it is towards you, and these hydrogens are on the plane of this board or your paper. The bond angle is 109 degrees 28 minutes exactly. Okay, so that is for shape of methane molecule in 3 dimension. Then moving to the next slide, geometry shape of molecules, shape of ammonia molecule. Now the ammonia molecule is a molecule containing lone pair also and as well as bond pair. Have a look at this. There is a lone pair. Now there is a repulsion between lone pair and this bonding pairs over here. That is why the bond angle has become lesser. It has become 107 degrees in ammonia molecule. So that is called distorted tetrahedral shape. It is tetrahedral, but it is still distorted tetrahedral shape. Okay, so that is the shape of ammonia molecule. You must remember the bond angle as well as the shape, name of the shape. Then moving to the next example, geometry shape of water molecule. Here molecules containing both lone pairs as well as bonding pairs. In water molecule, if you see OH, there are two lone pairs. Okay, there are two lone pairs, and this lone pair repulsion is maximum. Repulsion is maximum, because of which the bond angle, it is decreasing very badly to 104 degree 4.5 degrees. It is repelling. They are repelling these bond pairs very bad. They are repelling each other also. Okay, they are repelling these bond pairs also. That's why the bond angle has decreased from 109 degrees 28 minutes to 104.5 degrees. So that is because of repulsion, lone pair repulsion. Okay, now, so this concept of VSEPR theory, it is clear to all of you. Is it clear to all of you now? Is it clear to all of you? I am asking you the question. The concept of VSEPR theory, and with the help of VSEPR theory to predict the shape of molecules, it's clear. Okay, is it clear? I'm asking the question. Any response from your side?
Yes,
Okay, so now I think it is the right time for you all to begin with the next topic, which is called hybridization. And hybridization in chemistry means mixing of atomic orbitals. If you go to biology, hybridization means mixing of different, different trends, different traits. If you marry someone from some other community, if an Indian is marrying a Chinese, if an Indian is marrying an, some other, what you call trait family, then the offspring, biologically, they become wiser, they become more intelligent with higher IQs. Okay, that is mixing, intermixing of communities. Okay, intercaste, okay, inter social, all those things happening over there. But here in chemistry, hybridization strictly means mixing of atomic orbitals. Are you getting it? Hybridization strictly means what? Mixing of atomic orbitals. Now have a look at the next slide over here. The definition is on your screen. Hybridization, it is defined as the phenomenon of intermixing of atomic orbitals of comparable energies. There should be less energy difference between the orbitals which are mixing to form a set of same number of new orbitals of equal energy, and they are identical in all respects. Suppose if you are mixing orbitals, s orbital, p orbital, or a d orbital, s orbital is like this, p orbital is like this, p orbital, and d orbital is like this, d orbital. Okay, so they are they have energy difference, but the energy difference is less, slightly higher. So if you mix this, it can be made possible in so many ways. We can have sp hybridization, we can have sp2 hybridization, we can have sp3 hybridization. If 1s and 1p means sp, if 1s and 2p becomes sp2, if 1s and 3p orbitals mix, it becomes sp3. And we can further extend this, we can make it dsp2 also. 1d orbital, lower d orbital, d orbital I can have 3d, lower d orbital, one of them with 1s and 2p can form dsp2. Then we can go still higher, sp3 also d, sp3d, that means 1s, p3 and 1d from here, that is sp3d. Then we can still have higher, sp3d2. Then we can still have one more, sp3d3. So many hybridization we can have by allowing the orbitals to intermix with each other. So this is called hybridization. So now it is exactly time up for today's class. So I would like to stop my class over here only, so that I can continue in detail with regard to hybridization. I will try to explain hybridization in the best possible manner for you all, so that this remains in your mind for a long time. And once you have understood hybridization, then only it will facilitate and help you in understanding the next topic in this chapter, which is the most interesting and the most important topic in this chapter, which is called MOT, which is called molecular orbital theory. So please hang on over there, because I need to record your attendance
Yes,
also.
sir.
I will record your attendance, and after that only you will leave the class. Am I clear? Am I clear, my dear boys?
Yes, sir.
Okay, that's
Yes,
Yes,
sir.
Yes,
that,
sir.
sir.
Yes, sir.
that is fantastic. So
Yes, sir.
I hope today's class was interesting. Okay,
Yes,
now
Yes,
sir.
sir.
I will record your attendance. I will record your attendance in a while. Okay. Okay. The attendance is downloading. The attendance is downloaded. So thank you so much. Have a nice day.
Thank you, sir. Bye bye, sir.
Thank you, sir.
Sir, bye, sir.
Sir.